I will begin here. All right, so thank you everyone for coming today. It's a pleasure to welcome members actually of the Jochim group in Heidelberg, including Selim Jochim himself, Philip Price, and Marvin Holton. The Jochim group for many years has been trailblazing in the field of few to many body physics with fermions. In fact, I recall as a graduate student poring over their students' theses and master's theses, and actually sort of awaiting their group's next results. They've realized a number of landmark studies in 2D fermionic gases, new methods for distilling low entropy fermionic systems, as well as really neat novel detection techniques, more generically useful for ultra cold gases. So with this shared talk today, I think we'll hear several of these results. So please join me in welcoming Selim, Philip, and Marvin. Just as a reminder, the speakers will be available after the talk for discussions. Students and postdocs are strongly encouraged to join, and we welcome faculty for the first 10 minutes of that discussion. Finally, for our newcomers, please remember that you can ask questions via the Zoom Q&A or the YouTube Live, or if for some reason neither of those is working, you can email one of the panelists. All right, thank you.
Okay, good. Adam, thank you very much for the very nice introduction. And of course, thank you very much for the invitation to present our results here. It's a great pleasure, and we thought it could be a good opportunity to try, within this new format, also try a little bit different way of presenting stuff. And I thought it would be nice that some group members will together with me share all the results that we had in the last years. So what we'll be speaking about is juggling with single atoms to observe many-body physics. What you see in the background here is a visualization of correlations present in a system of three indistinguishable fermions trapped in harmonic potential. So with details you will see later in the talk. So what is it exactly that we are striving for? I mean, if you think of many-body physics, the most simple system that you can look at or can think of is really a Fermi gas. And if it's weakly attractive, that means the scattering length much smaller than interparticle spacing. It's basically an ideal Fermi gas, first of all. Yeah, not many external parameters, not many quantities actually do change so much. But if you look at it very carefully, you will see very tiny correlations that actually make a big difference for the state that you have. For example, and that will only be the case in momentum space. For example, just take one atom here. It's going to find a partner on the opposite side of the Fermi momentum distribution, and that will be the case for most of the particles that you find. So this kind of scenario is actually well understood. But of course, things change quite a bit as soon as you make the scattering large or infinite. No? In principle, still you could argue the system is more or less still the same, because still there is no other length scale beside the distance between the particles, which would then again correspond to more or less an ideal gas, but it's not quite the case. The understanding is indeed challenging. It has been extremely fruitful to study this as an ultra-cold gas system with lots of different techniques used to probe the system, starting from looking at the coherence properties, collective modes, radio frequency, Bragg spectroscopy, whatnot. But what I should say here is that all these methods that were employed so far, mostly or almost all of them are really looking at macroscopic quantities or individual single particle properties, not really looking at many particle correlations that we somehow have a feeling are necessary. It might no longer be sufficient to just look, for example, at pair correlations, but maybe we would have to look at 3 particles, 4 particle, and even higher order correlations. Yeah, and so for this reason, it has been like a goal for our group to somehow detect each and every individual atom's been resolved, momentum resolved, to actually get a clue and a handle on this. In many ways, this is very much the same as has been pursued with quantum gas microscopes, where you specifically look at the real space distribution of the particles. So how do we reach the many-body limit from a few-body system? Of course, in a few-body system, you always have a discrete energy spectrum and a very and basically, in principle, fully characterized just by only the energy levels. You will find things like a shell structure, both in atoms and in nuclei. And now our quest is here to go and bring such systems into a regime where you see things like phase transitions. You will have microscopic observers like a pressure, a microscopic phase, and so on, collective behavior. And to see these kind of things make the systems big enough. Yeah? There's been a lot of pioneering work by Peter Tönnies, who put molecules inside little helium droplets to and use these little molecules as a probe of the collective behavior of these droplets. In this way, find understanding how small you can make these droplets until, for example, superfluidity will be gone. So before I start presenting, or before we start presenting things that we've been doing recently, I want to just quickly introduce some of the experimental techniques that we are using for this. The first is to actually prepare small and very low entropy samples. And the basic idea behind that is absolutely simple. If you look at a Fermi gas and you look at it here in the momentum space, then of course all the excitations are at the edge of the Fermi sphere. So if you had somehow an idea how to just cut off the edge, then everything would be basically at t equals 0. And the question is, how can that be done? Yeah? And well, of course, there's no Maxwell's demon, but if you make the system small enough and you precisely control the potential in such a way that you only have a fixed number of bound states remaining, then you go prepare your Fermi gas in a little trap, and you tilt your trap using some magnetic field gradient in such a well-controlled way that, for example, in this case, 3 bound states are remaining. And if you do this well enough, such that really the remaining particles are not heated in the process, you end up with a discrete number state system that is also in the many particle ground state. You control all the degrees of freedom of that system. So that is one of the major ingredients to make all the stuff that we are going to present to you actually work. The other part is to actually have some single particle detection scheme that allows us to measure the position of particles in real and in momentum space. And the idea here is really, in many ways, maybe simplistic, but also versatile. It's just that we collect enough photons in a short time before the atoms have moved due to light scattering over substantial distances. So in this way, we collect about 25 photons or so from one atom, and the only real thing for this is to apply a counterpropagating resonant laser beams and a very large numerical aperture lens. So what does that look like if you take raw images? That's just the background exposure of the electron multiplying CCD camera that we are using. And you can see there's actually very few pixels that actually already have a signal before there's an atom. If we have an atom, it looks like that. Just zoomed in on the one atom. And so from this, you can already clearly see there's an atom. There's another atom here. And if you take many, many shots, you can see that here, just by the bare eye, you can identify most of the time we have an atom. And then in very few cases, the atom is missing, which you can also clearly identify here. Okay, what does our setup look like? I mentioned already the high numerical aperture lens, which we use to project customizable tweezer beams. There's a spatial light modulator that allows us to vary the size of that tweezer by between 1 to 5 microns. Then there's also AODs available to actually produce arrays of tweezers, in this case 2 or 3. And then there are 2 laser beams coming in from the side, which we can use to produce 2-dimensional samples together with that tweezer from the top. We can actually produce potentials that look a little bit like a cookie, and we are able to trap all our particles in exactly one of the maxima of this intensity distribution here in the vertical direction. So most of you are familiar with these kind of experiments. Our experiments that we employ for the things we are showing look like this. A lot of optics, a vacuum chamber, and so on. You know all of that. And what we are going to show you now today is 3 different things. The first part is, if you want, the most simple thing, but in this sense also, I think, very beautiful. We just look at more momentum correlations of localized fermions, localized in individual tweezers, and then we look at the momentum distribution. And it's in many ways, indeed, a realization of the hand-ray-pound twist experiment with fermions. In the second part, we actually then delocalize the fermions in a single harmonic potential, and then find structure in the momentum correlation of these particles, which can then be identified as what has been named Pauli crystals. Third part is that I should have mentioned here, really all these experiments actually conceptually very simple. There's even interaction deliberately turned to 0. We then dial in the interactions and look at what happens at this very small systems in a spectroscopic way. And in spectroscopy, we can find some non-monotonous behavior of the excitation spectrum as function of interaction strength, which we can then relate to a precursor of a phase transition and actually a long-lived Higgs mode. So this is basically the setup of our experiment and what we're going to tell you about. I will now hand over to Philip, who will take the next part. If there's any questions on the setup, you may also post them already now.
Sorry about that. Yeah, there's actually one question that I'll quickly ask here while Philip makes sure that he is all set to go. And that's a question from John Simon. He asks, could you implement a Maxwell daemon to implement cooling? The idea would be to expand in a really shallow, really harmonic trap for a quarter cycle and then blow away high momentum particles. And then another quarter cycle later, retrap in your original trap.
So you want to do the whole thing dynamically. This is somehow, so I'm not quite sure what is exactly the advantage. I mean, you want to make the cut actually momentum space, just like what I described in my motivation slide. Yeah, that's how you came up with this idea. If that can produce lower entropy than what we are currently doing, I'm not sure. Well, I mean, it will still be selecting certain momentum modes. Yeah. So I'm not sure what. Yeah, for some aspects, especially if you don't need to cool. I mean, this would not be cooling, but really just selecting particles. It could work well. Yeah. I mean, that's also the Maxwell's daemon is indeed this. I mean, it's actually selecting the particles that you prefer to have. Yeah. Mm-hmm.
Okay, and I think we don't have any others, so why don't we keep going? Yeah, and I think more stops works well too, so it's great. Why don't you go ahead, Philip?
Okay, yeah, so hi everyone. So I'm gonna pick up here and actually show some of the experiments that we did recently using the tools that Selim just introduced to you. So namely the capability to deterministically prepare few fermion states in optical tweezers and the capability to detect individual particles in free space, which allows us to really detect particles after a time of flight so that we can read off momenta of individual particles. And in this part of the talk, I'll be focusing actually on non-interacting systems, so systems that are conceptually quite simple, but for which we now have basically a new way of extracting coherences, correlations, and so on. And so the first experiment that I will discuss along those lines is actually meant to really highlight kind of the role of fermionic exchange statistics in our few-body systems. And so a nice way of seeing the impact of quantum statistics is actually to look at second-order interference, which is of course very well known kind of from the golden days of quantum optics. And a classic experiment in this realm is looking, for example, at second-order interference between two single photon sources, as shown on the left here. And what you find in these experiments is that the two-particle coincidence rates actually depends on the separation between the two detectors, and you can very clearly see kind of the unique signature of the bosonic statistics of photons in the bunching behavior of light that you detect in the far field of these two interfering sources. And so what we wanted to do in our experiments is to look at a similar situation, but now instead of looking at sources that prepare massless bosons, we use deterministic sources that prepare massive fermions. And so the way this works for us is that we can use two optical tweezers, as shown here, and using the techniques that Selim outlined, we can actually prepare an individual fermion in the ground state of each tweezer. And so these two fermions will be spin polarized, so they won't interact. And so this initial state is a very simple state where we just have these two individually localized fermions. And now to get these two particles to interfere, we can just switch off these two optical tweezers and let basically the wave function of the two particles expand, not in free space in this case, but inside an optical dipole trap that just confines the two particles to this kind of wave, this tube-like waveguide trap that is shown here. And now if we want to look at correlations between these two particles, at the end of this time of flight in this waveguide trap, we can take this single particle resolved fluorescence image as shown here, and we can read off the two coordinates of these two particles, which reflect their positions after time of flight, or equivalently their initial momentum. And so this is now very much akin to looking at correlations between two detectors in the far field in a photonic interference experiment. And so if we're interested in two-particle correlations in this system, we can start actually creating a histogram where we look at the momentum of the second particle versus the momentum of the first particle. And each image like this here gives us one data point where we read off the two momenta of the particles and basically enter a point into a histogram. And so if we repeat this many thousands of times, we can build up statistics, and we see a two-particle momentum distribution like this one here. And it's very clear that the momenta of these two particles are not independent. Like they're very clear correlations between the momenta of these two particles. First of all, you can never find two particles in the same place, so with the same momentum. So the diagonal of this two-particle correlator is empty, and there are actually these fringes in the difference coordinate between these two particles. So this means these particles avoid each other very strongly at particular distances. And what I actually find quite striking here is that the spatial scale for this is pretty large. This is 150 microns here, so this two-particle wave function is actually 500 microns across. And so these two fermions that are not interacting really avoid each other on a scale that you could resolve with the naked eye. Now, where does this come from? Most of you are probably familiar with this idea that these correlations, this anti-bunching that we detect in this case, is really a direct consequence of the fermionic statistics. And a way to see this is to look at what happens if you have two sources emitting indistinguishable particles and two detectors where you're looking for coincidence cliques. Then it turns out if you want to know the total rate for some outcome here, you actually have to sum up all the paths that connect the initial state with the final state. And in this case here, for the two particles, you get these two sets of paths. One of them has an exchange of two particle coordinates, which for fermions, it introduces an additional minus sign and actually leads to destructive interference between these two parts of the propagator here, and generically gives rise to fermionic anti-bunching. And so this is actually quite strong in this situation here. We have an interference contrast of about 80%. And so, you know, in some sense, this experiment really verifies that that we have sources with high purity, and we can directly see the fermionic statistics of the particles that we're working with. And so this is nice, but no, there's no reason to stop at second order. We can actually ask what happens if you introduce more particles to this type of experiment, right? And so this is pretty simple for us. You know, for example, we can just take a third tweezer, also on this waveguide trap, and load it with another fermion, so we can introduce controllably a third fermion in this interfering system. What we're going to be able to look at are these three particle correlation functions here, which are actually already becoming a little cumbersome to visualize. So a useful quantity to look at is actually this third order correlator here, which essentially integrates out the coordinate of one particle, and it just tells you after time of flight how likely are you to find the three particles in a particular configuration, you know, with distances d1 and d2 between the three particles, and all this relative to a random distribution. And so we can build up this third order three particle correlator, and it looks like this. One way to read this diagram is that you can think of the first particle sitting here, and then you're just plotting the probability of particular outcomes versus the coordinate of the first particle in this direction and the second particle along that direction. Now you can see there's actually quite a lot of structure in this third order interferogram. These stripes here arise because two fermions can never be in the same place. But even here, there's a lot of structure in this interferogram. And now, when we looked at this, we actually wanted to understand, you know, is there really something sort of intrinsically new going on at third order, or is this just basically the two particle interference that we already had at second order? So, I mean, these are non-interacting particles, so it's actually pretty easy to write down what types of correlations you expect, basically using this kind of same logic that I showed before. And I just want to point out, you know, drawing these diagrams is really just a means of basically visualizing the terms that you have in your propagator, or in the propagator describing the time of flight. And so if we have three sources and we're asking about correlations between three detectors, there are several paths that contribute to these outcomes. There's this direct path here. There's a set of paths where two particles exchange. And there are particular paths where actually three fermions are involved in an exchange. And now it's very clear that, you know, these types of interference processes you can already see if you're looking at second order interference. Whereas these processes down here are really new if you're looking at interference in third order. So you can say that these types of processes are really intrinsic to the third order correlate. Now, experimentally, we wanted to see whether this is happening in our experiment and whether we're too sensitive to these kinds of terms. And one way to do this is to look at the full correlator and actually subtract out the correlations that you know are there from the second order correlations. So basically removing these paths or the contribution of these paths where two particles exchange, and then you're left with only what would be the intrinsic third order correlations. And so this is what I show on the right here. Now you can see, in this case, these intrinsic third order correlations are still quite strong, and in particular, they actually contribute kind of quite a lot of the structure that you see in the full third order correlator. And so, this was a nice experiment for us to see that we can still see this kind of ideal fermionic behavior that that arises from the interference between indistinguishable particles at third order, and it also validates kind of our experimental toolbox for us. So it tells us that our source is high purity, that the time of flight works as expected, and that we can indeed extract higher order correlations using this single particle imaging in momentum space. And so, the states that we've looked at so far, or that I've been showing so far, are quite simple, as I mentioned in the beginning, right? So our sources in this case were these single particles localized in individual optical tweezers. So the initial state is just a very simple state of one particle per site in this tweezer array. And where we'd like to go in the future, where this can become more interesting, is actually if you have more complicated states as a source for a kind of for this kind of time of flight experiment. And where we would like to go is towards these two-dimensional fermionic systems that we've been looking at. So systems where we have interacting fermions in two-dimensional traps, where particles are delocalized, they're on top of each other, they can interact, and we can generally have interesting kind of many-body effects. And so this is a target for us, but we wanted to do this in a controlled way where we really maintain the exquisite control that we have over the quantum state that we have in these low dimensional systems where we're working with like 1 or 2 particles, let's say. And so what we worked on a lot in the last year or so is to actually establish the same kind of control, so really control over the full quantum state for two-dimensional systems with increasingly large particle numbers. The way we do this is that we create these kind of cookie-shaped traps using a tweezer focused to about 5 microns and an optical lattice, where we choose the parameters such that the trap frequency in the vertical direction is 5 to 10 times the trap frequency in the horizontal direction. So we're realizing these kind of mesoscopic, small, two-dimensional systems here. And so to control the quantum state that we prepare in these small two-dimensional systems is actually analogous to what Selim showed in the beginning, and that in that we want to fill these traps initially with a thermal sample, but then try to really get rid of the thermal part that we have in the trap and just hold on to the few particles that are sitting at the bottom of the potential, which realize the ground state if we can controllably remove all the particles that are carrying the entropy in the system. And so we typically initialize these small 2D traps with, say, about 20 particles at the end of our evaporation sequence. And then what I'm showing here is just the mean atom number at the end of this sequence, where we're just reducing the optical trap depth further and further in the presence of a magnetic field gradient. So we're starting with 14 particles here. And then as we reduce the trap depth, you see that the mean atom number goes down, as you would expect. But it doesn't do that in a continuous fashion at all. It really shows a very sort of pronounced step-like behavior. So here on these plateaus, the mean particle number is actually very insensitive to the final trap depth. And we also see that if we look at the fluctuations in the prepared particle numbers, each plateau here actually coincides very well with a region of dramatically reduced fluctuations in the particle number. So here we can really precisely dial in how many particles we have in the trap. And so it's actually pretty easy to understand where these steps come from if you recall what the energy levels structure for a two-dimensional harmonic oscillator looks like, right? So we can describe basically the single particle energy levels in this small two-dimensional trap here with a level scheme like this, where we have levels spaced by the radial trap frequency, and we have degenerate manifolds, the degeneracy of which actually increases as we go to higher energies here. And now what happens when we load in particles here and we reduce the trap depth is essentially that we bring in the Fermi edge shown by this blue bar here, and lowering the trap depth just means that we're basically pulling down the Fermi edge. And whenever the Fermi edge passes through one of these manifolds here, we actually lose all the particles sitting on this manifold, which corresponds to the steps here. And whenever the Fermi edge is between two manifolds, you have a region of very stable particle number, where basically the shells below the Fermi edge are completely filled and the ones above are completely empty. And so it's then easy to understand why these plateaus are so stable. And indeed, in the experiment, it works quite well. So 6 particles we can prepare with 90% probability. So this corresponds to filling the lowest and the first excited shell, and 12 particles corresponds to filling the lowest 3 shells. We can still prepare with 75% probability. And yeah, the the reason for this stability is the closed shell configurations, which is actually also what you have, for example, in noble gases, right? These are very inert, which is related to the closed shell configuration of their atomic electrons. And so in some ways you can view these closed shell configurations that we prepare here as kind of the cold atom 2D analog of helium, neon, argon in your periodic table. Okay, so this tells us that we have kind of full control over the ground state in a two-dimensional trap. And we now want to apply the same trick that we used before to use this single particle resolved imaging in momentum space to learn something about the microscopic correlations between these particles. And so again, we can confine everything to a two-dimensional plane, let the particles expand from the tweezer and take an image in fluorescence to resolve the position of individual atoms after time of flight. And so the case that I actually now discuss goes back to these non-interacting scenarios where we're just thinking about a single spin component, say 6 particles that fill the lowest 3 shells here that are all spin polarized and that are non-interacting. So it's again a very simple state. But now there's some kind of a curious thing here that if you're in this harmonically trapped system and you expand this in another harmonic trap, then actually what happens is that the densities and the densities correlations after time of flight are the same that you have in trap, right? So if we look at an image like this after time of flight, this actually corresponds exactly to in situ, so real space configuration that you would be able to see in the trap if you could resolve individual particles. And so you can see that this is a new regime here that we can basically prepare a continuum system with several particles where the wave functions are overlapping, but we can basically essentially have a resolution to probe the system below the interparticle space. And so this is quite exciting. And we can now ask, can we actually see structure looking at this pattern that we see after expansion of these 6 non-interacting fermions? And so this is the image that I just showed you, where you see 1 particle on the center and 5 particles on this ring-like structure around it. You see that the configurations that you see actually vary quite a lot, but this kind of pattern shows up several times. You can see it here, and in other images here. And so we wanted to know, is there really some structure there? And a pretty simple way of looking for patterns in these images is to actually just try to align them in a clever way. And so we're using an analysis that uses 2 processing steps. For each image, we actually find the center of mass of the 6-particle configuration. We just shift the image to align the center of mass of each individual image with the center of our region of interest. And then in a second step, we actually apply a global rotation to this image where we align the mean angle of the particles in this particular image to some reference axis. And so what happens if you do this for many images and put them all on top of each other, you find something like this. So even though the system itself is rotationally symmetric, I mean, we're working in a rotationally symmetric harmonic trap, when you draw samples from this wave function and you put them on top of each other and you align them in this way, you actually find very clear structure. You find this pattern where we typically have 1 particle at the center and then 5 particles on a ring surrounding the central particle. And now again, these are non-interacting particles, so it's a bit surprising that you see any kind of structure here. But you have to remember that again here the Pauli principle applies. So these particles are trapped in a harmonic trap, they're confined, and they can now reduce their energy by basically avoiding each other by as much as possible. So this is again enforced by the antisymmetric nature of the wave function. And so it turns out that the ground state of these 6 non-interacting fermions in the trap is such that the particles tend to sit in this kind of pattern. And we can then resolve this if we by drawing samples from the wave function and looking for this type of correlation. Now, you might be a bit worried that this could be an artifact of this imaging procedure, right? After all, we're sort of aligning all these patterns, and so you might expect to find some structure. So an important check that we did for this is to try to actually remove those correlations. And one way to do this is to just introduce additional energy of the system. So we can do this by introducing some trap modulation, which just kind of heats up the system. And then you see that, as we introduce energy to the system, the correlations actually go away. So these are really a feature of being close to the ground state in this fermionic system, and even introducing around 1 h bar omega of additional energy basically makes these correlations go away. So yeah, this is really a unique feature of having a few particles confined in this trap with the fermionic exchange statistics. So we have been looking at these patterns. I've showed you mostly the 6-particle case. We can also look at the 3-particle case, where instead of this flower-like pattern, we find this this 3-legged star here. But this is yeah, I think it's kind of like a kind of cute phenomenon that we can see this structure in this non-interacting system just given by the quantum statistics, which is maybe not something that you would have expected intuitively. I should say that the idea to look for these patterns goes back to Mario Schreider and his group. So they proposed this a few years ago and coined the term Pauli crystal for this type of pattern because it's really given by the Pauli exclusion principle and by the fermionic exchange statistics. And so we reported on the observation of these Pauli crystals a few weeks ago. But I think the really important message of this is that with this kind of technique, you can really look at kind of the microscopic details of a continuum system. So we can basically resolve what the environment is of an individual particle in a continuum system. So this would obviously be a very nice tool to look, for example, for the environment of an impurity in a Fermi sea or something like this. So it gives us this microscopic access that we know from optical lattice systems now for continuum systems. So this is what I wanted to say about these non-interacting free-body systems that we've looked at. I'm going to hand over to Marvin, but I'm also happy to take some questions here.
Great. I have several questions here lined up. So the first question is from Bill Phillips. And this goes back a little bit to the beginning of the talk as well. The question is, you talked about collecting enough, but not too many photons from the untrapped atoms in the momentum resolved microscopy. But if trapped in the Lambdicki regime, you can scatter more without changing the center of mass state. What choices do you make here? Or I think he's asking, how do you balance those two considerations in this case?
Yeah, so basically, I mean, that latter approach of trapping the particles in a very tight trap is basically what you do if you want to image these particles in an optical lattice system, for example, in a quantum gas microscope, right? Then yeah, you would want to work in this Lambdicki regime. Basically, we're choosing this approach because it's technically very simple, right? I mean, you just need to shine in some resonant laser light, and that's really all you need. You don't need any deep traps. You don't need Raman sideband cooling. It's a very simple and versatile imaging scheme. For example, it's very easy to make this spin resolved. Now, we haven't shown this here, but we can actually take 2 exposures in the same run that are just separated by 50 microseconds or so, and where we're using the fact that the transitions are almost closed in a high magnetic field. So it's very simple to make it spin resolved, for example, which is maybe harder in other approaches.
Great. The next question here is from Monica Gutierrez. She asks, have you tried using principal component analysis to analyze your images? We've tried many things actually to analyze these raw images. What I've been showing here are just low pass images, right? So the original image is binary, so where we detect individual photons. We just do a very simple thing and low pass and look for peaks. We've really tried many different things. They all give kind of roughly the same performance. So this turned out just to be the simplest thing. I think the peculiar thing is here, because you have so few photons, and because the atom can still move around while it's being detected, actually the shape of each atom signal or the shape of these atom signals can be very different. It can be very kind of rugged and irregular. And so that makes it actually a little hard to use other peak finding algorithms, I think. That's kind of an ongoing challenge, actually. Okay. And then I think 2 more quick questions here, and then we'll switch over. The first one's from Adam Kaufman. He asks, does the spilling procedure prepare the many-body ground state?
Yes, yeah. I mean, that's the idea, right? So we go to a regime where interactions are off or basically very weak. And then, so I'm just taking this example here. You're allowed to put one singlet, so one to spin up and one spin down particle in each single particle eigenstate here. And so the state that we prepare at weak interaction is actually the exact ground state. So you have a singlet on each.
So the Q is always much smaller than the trap frequency here.
Say again?
The interactions are always much smaller than the trap frequency.
Yes. Yeah.
At this during this point.
You can then turn it up, right? I mean, then you have the ground state, then you can switch on interactions.
Got it. Okay. And then the next question is, I'm going to combine 2 actually. So the question is, did you examine the 4-particle correlation, or more generally, what limits going to higher order correlation functions? And given that there might be challenges, are there other things that you might consider measuring at that point?
Yeah, so I mean, looking at these higher order correlations is challenging. Typically, mostly because of the statistics actually that you can collect. So the images that I showed for this 3rd order correlator, that's like 50,000 images. We had to run the experiment for a couple of weeks for that. So really going beyond that, is going to be quite challenging. Now, I would like to point out that basically the coincidence rates that we get are essentially the same that you get in photonic systems. So our experiment is much slower than photonic systems, but efficiencies are much higher. So you end up with like roughly the same rates. So I think in some sense, we can actually do better potentially than photonic systems once we start talking about more particles, more detectors, and so on. But we're also running into a regime where just the statistics are going to make it hard to look at anything much higher than like 3rd, maybe 4th order.
Got it. Okay. All right. So I think we should switch over to Marvin then. Thank you, Philip.
Okay. So let me start the 3rd and final part of the session. And yeah, as you have just seen in the first 2 parts, Philip, already non-injecting fermions can show some really interesting results, and are also a really useful tool for us in order to benchmark our experiment and our experimental capabilities. But I think it's also clear that in order to really introduce complexity now, and in order to observe effects like phase transitions and collective behavior, we really need interactions again. And interactions in our case are contact interactions. So we have spin up and spin down fermions, and these interact. And now in 2D, we have the very special situation that there's actually a bound state present at any attraction strength that we use. And we make use of this bound state. Namely, we use its binding energy EB in order to characterize our interaction strengths throughout this talk. And then there are also 2 other important scales of the system. These are again the trap frequency. This leads to some single particle gap in the spectrum. And then finally, we have the Fermi energy or interparticle spacing. And for now, we will only consider systems that are quite small, and where the Fermi energy is basically still on the same order as the trap frequency. So we can ignore this for now and just look at these 2 scales. But this already leads to actually a very interesting situation, because on the one hand, you have the binding energy, and this binding is required since we have fermions in order for a superfluid to form. And the superfluid is a very interesting system on its own, as Selim has told you in the beginning already of this talk. And on the other hand, we have this single particle gap and this shell structure. And if we now look at this very special case of a closed shell, then actually all the states here are already occupied by fermions. So there's actually no way for these fermions to form a pair unless they overcome the single particle gap. So we have this competition between the single particle gap and pairing. And this is actually now believed to lead to a normal to superfluid transition. And this transition is exactly what we now are interested in. So we really want to study this transition at the most fundamental level. So starting with the smallest possible instance of the system, which is really just 2 particles in the lowest shell. And then we really want to go and fill each shell up one by one. So going to 6 particles and then to 12 particles. And then we want to answer questions like, how many particles do we actually need to see something like this phase transition? And what does a phase transition even look like at these low particle numbers? Or what does the few body precursor of a phase transition look like? And yeah, so how can we study a system like this? Philip has already mentioned the connection to atomic systems, to noble gases. And so we can also now make use of a technique that works very well for atoms, and this is spectroscopy. So what we do in our case is we start again from the ground state of the system. So for example, here you have the 3+3 particle ground state, and then we drive the system by modulating the binding energy at some frequency. And this leads to monopolar excitations of the system. And then after some time, we just spill to the ground state again. So we remove all the excitations again. And then we just count how many atoms are left. So in this case, we would see there are only 5 atoms left. So 1 single atom was excited. And by just repeating this many times, we can again get access to the full spectrum, basically. So here you see one example where we shake at a frequency of 2 kilohertz, and you see most of the times we actually remain in the ground state. If you compare this to this other measurement here at a slightly higher frequency, then you see that now suddenly a lot of times we're actually removing 1 or 2 particles from the experiment, from the ground state. And now we can repeat this at many different frequencies, and in this way we get the full spectrum. So here now on the x-axis, I plot the excitation frequency, and on the y-axis, the atom number. Again, 6 atoms means we remained in the ground state, 5 atoms means 1 atom was lost, and so on. And what you see here is that this spectrum actually has 2 very clear and distinct features. And let's start with this feature here on the top, because this is actually quite easy to understand. So what you see here is that most of the times we lose 1 atom, sometimes we also lose 2 atoms. And these are exactly single particle resonances. So what's happening here is we take 1 particle out of this ground state, move it up by 2 shells. To do this, we have to pay 2 times the trap frequency, which is marked by this red line here. But then, since this measurement is already taken at a finite binding energy of 0.3 in units of the trap frequency, we have to pay some additional energy. And this is just because the ground state here is a little bit denser than this excited state. So we basically have to rip out this 1 atom here. And this is basically just a mean field shift of energy that we have to pay in addition. So we see the energy that we need to pay is a little bit larger than 2 times the trap frequency. But now, other than this simple single particle resonances, you also see this second feature. And this is actually now much more interesting, because what you see here is that we are always losing 2 particles at the same time. So there's never 5 particles, but 2 particles are always lost at the same time. And here the picture is that this is really corresponds to a pair excitation. So 2 atoms are excited at the same time, and they are going up 1 shell. And again, we expect that this costs in a non-interacting system 2 times the trap frequency, but for some reason we can now gain some energy by this process. So this looks like a very interesting effect, and now, of course, we want to study this in further detail. And in the experiment, we're now in the lucky situation that we can basically tune all the important scales of the system. So now we tune the binding energy versus this single particle spectrum, the single particle gap. So what we do now is, now I plot one of these spectra basically along 1 column here. So this spectrum is now this column, and then I tune the binding energy on the x-axis compared to the single particle gap again. And here again, you have the pair excitation, the slow excitation, and then on the top, the single particle excitation. And what you see is that as we increase the binding energy, first, both of these effects actually get stronger. So we have to pay more and more energy to pull a single particle out of the ground state, and we gain more and more energy if we excite a pair of particles. But now, let's continue this measurement to higher values of the binding energy. And then what we see is actually quite interesting. As soon as the binding energy actually gets on the same order as the single particle gap, so basically when this picture of a shell structure breaks down, because the this single particle gap is not the most relevant energy scale in the system anymore. At exactly this point, we see that this lower pair excitation here has a minimum, and then it turns around and actually increases with energy again. And yeah, this is what we found. And now the question is, how can we understand this behavior of basically the energy of the ground state compared to this first excited state where we excite a pair of particles. And now we are in the lucky situation that actually the theory for this was already developed quite some time ago by Georg Brun. And he had exactly this system in mind. And also, I should really mention, he was the one who came up with the idea for this whole measurement. And what he looked at is exactly a closed shell system again, but this time really the thermodynamic limit, so the many particle limit. And he has studied, again, the lowest collective mode of such a system. And also here, the lowest collective mode is exactly the excitation of a single coherent pair across the single particle gap. And if you look at the energy cost of this as a function of the binding energy again, so this is plotted here on the right, you see again, we start with 2 times the trap frequency in units of the energy in terms of 2 times the trap frequency. And then as we increase the binding energy, the cost for exciting such a pair actually goes down and down further and further with binding energy, until at some point we actually hit 0 energy cost here. And at this point, the system becomes unstable. And we get a quantum phase transition from a normal to a superfluid. And if we now continue increasing the binding energy further, the lowest collective mode in a superfluid is actually the Higgs mode. So this is exactly this oscillation of the order parameter of the superfluid in this minimum here of the Higgs potential. And yeah, this was really what was developed in this paper here. And then this is now the many-body limit. And then later, Johannes Bierlein and Stefanie Reimann, again in collaboration with Georg Brun, they now also looked at the few-body case. And they have really now studied the exact system that we can also now prepare in our experiment, which is this ground state of 3 plus 3 fermions. And what they have done is they did an exact diagonalization, and then they plot all the excited states in the same graph here. And what you see is, again, there are a lot of single particle excitations. So these we saw in our experiment as well. And then there's actually a single mode that behaves very differently, that first goes down with increasing binding energy and then goes up again. And this is, of course, exactly what we also found in our experiment now. And I think from this plot here, the picture is clear. It looks like this is already something like a precursor of this many-body phase transition mode that we have down here. And to make this even more convincing, they then also included further particle numbers. So here is a calculation for 6 plus 6 particles that goes down even further. And then you see that also for 10 plus 10 and 15 plus 15, this mode converges further and further towards the many-body limit. And I should also mention that this is already in a regime where these exact organization is extremely difficult, and a lot of approximation already have to be done. So this is also, in some sense, a really nice regime for us as experimentalists, because predictions get very hard quite soon here as a function of particle number. Okay, and now I've already shown you our results, so we can really see that this is actually a pair excitation. So we saw that these are really coherent pairs that are excited, and we also see this exact behavior that this first goes down and then increases with binding energy again. But now, of course, the next question is, can we also see this convergence towards the many-body limit? And in order to check this, we have now also taken a run with 12 particles. And as you see, qualitatively, we see again this lowest mode here. And if we plot now both measurements in the same graph, you see that the 6-particle measurement here in blue is much higher in energy than the 12-particle measurement. So we really see this convergence towards the many-body limit. And so this is now really the picture that we have, that basically we have this pair excitation here that goes down further and further in energy as you increase the particle number. And at some point you would hit basically here 0 again, and then the system actually forms pairs spontaneously and we get a superfluid. And in this sense, we really observe this lowest or this lowest mode as a free-body precursor of the Higgs mode. And now there's one final thing I would like to tell you, if you take a look at the spectrum again, you also saw that this lowest mode is quite well isolated in energy, because it's the only mode basically that is below 2 times the trap frequency. And so this, we can make use of this, so we can actually try to only drive this as a 2-level system. And what we have done in this measurement is we have changed the modulation time and then always checked, are we in the ground state here in red, or are we in the excited state? And what we see is that actually we can excite this mode coherently. So we can now really take this already rather complex many-body system that has an basically unpaired ground state and supply the missing energy in a coherent way in order to get the system into this complex paired state. And I think this is really an amazing starting point now for future studies where we want to apply all our tools again of measuring correlation functions. And yeah, with this, I think I will hand over to Selim, and he can talk a little bit about our future plans before we then take some questions again.
Yeah, so for me, this is getting already pretty close to what really was my initial vision when we actually started preparing this tiny systems. So for me, it now remains to discuss, I mean, how far are we, where are we in actually reaching the many-body limit? And there I would like to first mention the last energy scale that Marvin had in his first slide. That's the Fermi energy. Yeah, and Marvin mentioned that in the current systems, the Fermi energy is not really much larger than the spacing between the shells. Yeah. Now, how would this look like if we were to think of the many-body limit? Yeah? In the many-body limit, a 2D gas would be described by the BEC.BCS crossover as you tune the interaction strength. If you make the interaction strength super weak, then you would end up being in the BCS limit. If you make the attraction really strong, you would end up in the BEC limit. And as Marvin said in the beginning, in 2D, any finite attraction will always produce a pair. So the interaction strength will be characterized by typically either the log of the Fermi momentum times the scattering length, or you can exactly the same way also parameterize it by the Fermi energy over the binding energy. So as soon as the binding energy dominates over the Fermi energy, that would be something you consider molecule-like, so you would be in the Bose limit. And if it's the other way around, the binding energy being much smaller than the Fermi energy, that would be the BCS limit. Okay, so what is now here, you would argue, because the attraction is so weak that even we don't have a superfluid at 0 temperature, that's what we were talking about with this phase transition, we should be like even beyond the BCS limit. Yeah? In this graph, however, of course, we have to be in the limit also where our shell spacing is negligible compared to the Fermi energy. In this case, we don't simultaneously realize. Yeah? So in fact, we're already somewhere here where binding energy is on the same order of Fermi energy, and then we cross right through the crossover without actually clearly separating the individual regimes. Yeah? But that would actually be something that could be really interesting to dive into a little bit more. But also, I would like to be, I would be super interested in understanding here the many-body physics with just really the observables that we developed and currently validated just with the non-interacting samples. I mean, the question really is, what happens if we actually don't only look at one single spin state, but we detect the other spin state which is present there too and die in some interactions? How will the correlations align? And obviously, if there's no interactions, there will be 0 alignment between the two spin components, and it will just be some random orientation. But then as the attraction grows stronger, at one point, the two correlations will actually lock in real space. Huh? So, but how will it look like in momentum space? Well, that's what Philip said for harmonic oscillators. The Fourier transform of a harmonic oscillator wave function will again be a harmonic oscillator wave function. But here it will now be slightly different because, of course, interactions will actually perturb these wave functions. And we expect that actually in this case the momentum distributions should actually be anti-correlated. So for finding for one particle in one spin state, and at this momentum we should find a particle on the opposite side. Well, I mean, what is actually needed now to see Cooper pairs? Actually, exactly that the Fermi energy should be like larger than the shell spacing by some amount, which we currently don't have. But we think if we have something like 100 atoms or so, then we should be in a regime where we see that. And obviously, the most interesting thing will not be to see Cooper pairs. We know they're already there, although it would be beautiful as a start. And then use this as a starting point to really try to understand the many body correlations that we somehow know are present in the strongly interacting regime. And with this, we would like to thank you for your attention. And if you, so this is Heidelberg, if you want to join us on our team, you can drop us an email here to me or to Philip. I would like to also thank our wonderful team who has been like really doing tremendously during the last months, also working during social distancing currently and so on. It's a lot of fun to work with all these people. Thank you very much for your attention.
All right, thank you everyone for the great talk. Actually, I really liked this model that you've now introduced us to. There are many questions. I'm gonna, with the time that we have left here, I'm going to try to get through some of them, but let me remind everyone that questions that I don't get to could also be asked in the discussion following the talk. So the first question is from Bill Phillips, and he asks, asking about a superfluid transition in the context of a superfluid transition in a small fermionic system, that concept is similar to the old question of how many atoms are needed for a BEC, a question without a clear answer. Is there a formulation of the question that's more clear here? Superfluidity is not the same as BEC, but they are related. Do all of these points sort of map onto the fermionic case as well? And just to be clear, this is in the case of a paired superfluid, not a molecular superfluid.
Yeah, I mean, indeed, I mean, all these questions, they were like, I mean, have already been asked by Peter Tönnies many years back, and he tried to answer them, and he did answer them for superfluid helium. So that was bosons. Yeah. In the strongly interacting regime, my first speculation would be that the size should be like the required size should be similar, or maybe even slightly smaller than for weakly interacting bosons. I mean, my personal take on this so far is always, I mean, what you call a superfluid, how you would define your superfluid to be. Of course, that would be critical velocity, some quantities of that kind. And in the end, it will, in most cases, I guess, boil down to actually how precisely you can actually identify a system as being finite, for example, observing its discrete spectrum and so on. I mean, we've been discussing this also, I mean, now observing like the precursor of a Higgs mode. I mean, if you were to ask for superfluid, I mean, Goldstone modes would be much more interesting. Yeah? So excitations of the phase. Yeah? I mean, do you have a coherent phase? For this, I would say the same thing applies that I already mentioned. Fermi energy needs to be significantly larger than the single particle excitations from shells. So you need a significant number of shells before you, I mean, have a chance to observe something of that kind. Yeah?
Got it. Okay, thanks. And then I'm going to try actually to organize to make clear which part of the talk these questions are targeting, so that if you guys want to share questions, you can do that. So this next question is regarding Marvin's part of the talk. So, and this is, should we be expecting any Goldstone mode associated with the rotational symmetry of the polycrystal?
Yeah, I think, I mean, Selim has already answered this question partly. I think the Goldstone mode is kind of there, but to really see it, you would need a system that is actually larger by some amount, because at the moment, actually, the pair size is on the same order than the system size. And the Goldstone mode is basically an oscillation or an excitation of the phase. But if the pair size is already one pair is as large as the system, it doesn't really make sense to talk about this excitation of the phase of the pairs. So I think this is basically the same answer. So we need a little bit larger systems in order to see a Goldstone mode.
Got it. Thank you.
There's one advantage here, if I may add something.
Oh, yeah,
I mean, the fact that you know, in 2D, the degeneracy per shell actually grows slowly. Yeah, so the number of particles per shell compared to, for example, a 3D situation, or that actually helps you there. Huh?
Got it.
So you know, the number of shells grows decently fast with particle number.
Right.
Yeah.
Okay. The next question here is from Nathan Shine, also on this section of the talk. And it says there's a second resonance in the data that starts out decreasing in energy with the binding energy and then rises back up, but generally at higher energy. Can you comment on what that is?
Yeah, that's a very good question. That's actually the first question that we have also asked ourselves. And so the reason is in this first theory proposal, they were only considering a completely symmetric harmonic oscillator trap. And then this modulation of the binding energy only couples to monopole excitations. But since our trap breaks this symmetry slightly, even though it's only around 1%, so we have 1% anisotropy of our trap, we also couple to other excitations, or basically also to quadrupole excitations. And this higher mode is basically a mode where we excite pairs that have angular momentum. So the lowest mode is 0 angular momentum pair, and the higher modes have 2 units of angular momentum, plus and minus. So these are actually 2 modes, but they are degenerate again. So we only see one signal in our spectrum. And yeah, these are these higher modes.
Great. And then I think we have time for one more question here, and this is actually from Philip's section of the talk. And this is actually I'm combining 2 questions here, one from Mehdi Hassan and also one from Bill Phillips. And the question is basically, what is the intuition behind the structure that one observes in these higher order correlation functions, and why do they occur in the first place? I think some of this you hit at, but exactly why the structure is what it is, I think is the nature of the question.
Referring to the first part, so the interference from tweezers, or these polycrystals where the particles are delocalized into each other?
I believe it's in the polycrystal section.
Yeah, okay. Yeah, so it's a little curious, for example, that you see, for 6 particles, you see 1 particle sitting at the center and 5 particles surrounding it. I don't think there's, and this, so if you go to larger systems where you have more shells, then you get even more rings, so you can get like really sort of like odd numbers of particles on these rings. I don't think there's a great understanding of why that happens. So it's clearly different from what you get in interacting systems. So if you look, for example, at what you have in in these river crystals that the Emanuel Bloss group realized a few years ago, there you would actually expect different symmetries. So the symmetries that you see do seem to be related to the fact that it stems from this exchange antisymmetry, but I don't have a good question for why you see those in particular.
Got it. Okay, cool. All right.
Maybe one comment from my side is also, if I may, just very quickly. There's no long range order in a Fermi gas, and so you don't expect, if you grow the system, to really see long range order over large distances. That's just what I want to say, and that's what you would actually call a crystal after all. So in that sense, the name is a little bit misleading, maybe.
Got it. Okay. All right. So with that, if you wouldn't mind unsharing your screen so I can quickly post for next week. Okay. And so next week, the Quantum Sciences seminar will not be happening because Europeans do this healthy thing known as vacation. Vamos will have Manuel Andres from Caltech with his talk entitled Quantum Science and Tweezer Arrays. And that'll be August 7th at 12 p.m. Pacific Standard Time, as usual. So let me just remind you that you can join us afterward with for a discussion with the speakers. Thank you.